Okay, here I'm putting the circuit board together. Still not finished. Have to put the triac here. But I'm not making a pre-made board. It's only going to be a one-off. So it's all done like this, just with wires soldered onto the circuit board like that, and a few wires on the top. And I'm about to drill and cut where I'm going to have the display. It's going to be there. I'm going to have the pot here. I'm going to have a LED here and a push button switch here. And I've removed the old connector. Yeah, the old connector here. These ones I had to cut the wires off because, and this I had to wrap a cable tie around these to press all these around. It's not a very good system to take this off. So you got to bend these and you got to get it out of the hole here. So I had to wrap a cable tie to bend these circle so it pushes out. And then I had to put a fiber washer here because it's slightly too big, the hole, for this plug. Okay. So that's that. And here's the front panel. So I've cut that. I've put the screen. I'll have to put some mounts, just glue it onto the plastic. I've put the LED hole, that's for the element heater. There's the pot. It's a very good quality pot, that one. And a double LED here. And the switch. Okay. So that's that. Okay, so I've got the, this is the part that I've got up to. I already showed this, yeah? But I just wanted to point out something here. A little bit of a criticism here regarding this Weller station. I just found they actually have no quality control when they build these here in Australia. Cooper tools, yeah. No quality at all. You see this is the AC mains coming in. So that's the active connector, okay, that comes in. That's fine. I've changed the earth now. I've done it through the connector there. Before it was directed there. In Australia, they would want it direct there, but I will not do it that way because this screw was loose here because it was only screwed on plastic. So it's no point. So I've done it through the connector, okay? But the main criticism is here. It's on the switch. So the yellow is the active, okay? And you can see the yellow is on the brown here, which is the active. And it goes to the switch at the top there. The bottom is the neutral to make the neon light up here. The middle is the transformer output. Okay, so when you press the switch down, you short these two. But have a look, they just used an auto plug here. And this auto plug is acting as an insulator just in case these wires decides to touch together here, which they're very close together, right? Yeah, there. I pulled them out a bit, right? I just put them back in because I had them off before, just to show you. But also, have a look at this. This is the transformer input, the active, right? So when I take this plug off here, when they crimp this, which is straight wire, it's a straight wire of the transformer. Have a look. It's actually loose. It wasn't crimped properly. Look at that. So that's the actual winding copper. Look at that. Okay, that's the factory did that. Yeah, so they didn't even bother here putting a cover, a little rubber boot on top of the spade sort of connector there, female. So I'll be redoing this, and I will be putting insulation, heat shrink, or a boot on top of these things. And that is safety. Not putting the earth, not putting the earth from here to there, safety. They think that makes it safe. It's quality control makes it safe. Okay? So, that's that. Okay, and here I'm just showing the internals. The display is mounted like that, with studs here glued to the back. Just 2 screws. Okay. The pot, I've changed it because the pot, I've realized it was a logometric pot. So I put a linear pot, 10K. And the LED there, and the heater LED behind there, inside there. The main switch wires, I have made them a lot better. I've put insulators here on top of the wires, redone them, changed the middle connector, and you can see there I have the programmer still hooked up on the serial interface here of the microchip. The circuit board is there. There's a lot of wires, but it all plugs. The triac, let me just remove this. The triac, I did not place it on the circuit board for the reason, right, if this is left on, for example, not cutting out, when I did some tests, it does warm up. It actually, if you leave it running for 10 minutes, it will actually heat up to 63 degrees. Maybe I should have used a better triac. It's I think it's a BTA12. But anyway, it doesn't stay on because it's off and on, yeah? Switching the element off and on, so it doesn't get warm, it doesn't get hot at all. But I've mounted it on the transformer there with a heatsink. And I put some insulation there, and then these wires go to the circuit board. And that's the board there, and the thermocouple board, I mounted it separate. So I've changed it again because the issue with this, you don't want this to warm up. So anything, if the board gets a bit warm and it's soldered to it, then it's going to pick up the heat from there because of the cold junction compensation. So the case here warms up. So I had to do another compensation for the cold junction here, and I had to minus 5 degrees from internal temperature to get it correct at the soldering iron. So that's what I did. The optocoupler is mounted there in front of the PIC chip, and the rest is what I showed on the circuit board. So that's the buck converter I've used, the ones you get from China. It's actually just loosened there. It cannot move. It's between this plastic here. I've set the voltage to 8 volts, and then I've got the 5 volts regulator on the board. So that's pretty much it. I did I put a proper fuse here. It had originally a inline fuse originally, but it was just soldered on. So this fuse can be changed. Okay, so I put a I think 2.5 amps or 2 amps. I think it's a time fuse what I put. I put a small little circuit board here, just mounted it there to this one is I made it myself with a pop rivet there, and to be able to do the connections for the AC, going to the triac and feeding the board. Okay, so that's that. Okay, so on the last video, if you recall, in the oscilloscope there, I had on part 6, I had those pulsing on the interrupt, and what it was the movement switch on the soldering iron. So originally I had this stuck on a vise and I wasn't really moving it, so I didn't pick up that that's what that was. I thought it was interference, but it was the actual sensing switch switching off and on, you know. Before I continue on with the software, I want to show you the circuit diagram just over here, because I have changed it slightly again from last time. So this is the final circuit, okay, that you're seeing here. And what I added a temperature sensor, just a cheap MCP 9701A, and I added an extra voltage regulator, a 5-volt voltage regulator that I didn't have before. I only had the one, and I will explain why I had to do that. So originally, when I was building the circuit board, I had a 12-volt regulator here instead of the buck converter. But after I ran it like that, I've realized that the heat was adding too much heat in the case. And once you have the cover on the case here and closed up, it was adding just too much heat for my liking. That voltage regulator, the 12 volts, even had a heatsink on it, was heating up to about 45, 48 degrees. So because of the AD8495, which got compensation for the cold junction here, which, by the way, it's a stupid idea. In my opinion, this compensation is absolutely useless. In actual fact, you'll end up having wrong results, because no one is going to install this in a perfect ambient case. So this was calibrated at 25 degrees at the factory. Now, anything, once the compensation, it's trying to sense temperature on the junction here, which they call the cold junction, where the thermocouple leads hook up. Now, in actual fact, my soldering iron, the thermocouple leads is inside the element. After that, it's not thermocouple leads. They're just standard copper leads. Okay, it's not really an issue. Okay, I know a lot of techs might tell you that it is, but it's not for this job, and I still got an accurate reading. So this, once the temperature around here goes above 25 degrees, this will start. If it's gone to 26 degrees, it will add, okay, extra heat, extra voltage, resulting in higher temperatures reading. So if it's gone up 26 degrees, it's going to add an extra 5 millivolts. Okay, it's gone up 2 degrees, it's going to add 10 millivolts extra. It's quite, I don't know who thought of this idea. This compensation does not help at all. It's actually a stupid idea. You could be measuring a 1,000-degree oven. Well, if this module, this chip is next to the 1,000 degrees, it's going to try to compensate for the extra heat, right? Which, again, it's actually doing the wrong thing. So unfortunately, in the original beginning, I thought this was a good chip, but when I've realized that the way it works, I realized it's actually not a very smart module at all. Now, that's what I've used now, and the way for me to solve that was 2 ways. One was to measure the temperature in the case here, in the soldering iron case, which I did, and was about 30 degrees. So I minused that of the 25 degrees that this AD495 will start compensating for. So, and that was working fine. The only problem with it, you have to wait maybe 5-10 minutes for the case to heat up to its running temperature to get the correct value out on the display. So then I thought, because I'm using this soldering iron, it has two functions. Okay, the beauty with doing custom work and custom design is you can make it run how you want, not how the manufacturers think we should have things. So my idea came to be that this soldering iron has two functions. One, as a soldering iron, and if I, just to show you here, set the settings to 0 degrees, okay, 0 degrees. Now this is no longer a soldering iron. Now this is a temperature indicator. So I can measure temperature with this, okay? And I can measure below 0 degrees. I can measure the fridge temperature. Pretty much like what this does, measure, you know, like a temperature indicator. But the beauty with this, it's got a solid part here where I don't have to worry about a flimsy thermocouple, okay? You say, well, why don't you use a normal temperature indicator? You can, but I came up with the idea to do that while I've got this on my bench using a soldering gun. If I'm not soldering nothing, I can actually use it as a temperature indicator. Maybe I want to measure, see what a transistor is heating up to. So because of that, okay, because of that, I thought, getting back to the circuit here, I wanted more accurate. I wanted to keep this AD8495 given the correct temperature, regardless of the temperature inside the case. Okay, so that's why I've added the MCP9701A. So I can, anything above 25 degrees, and that's around roughly where this starts compensating. If it adds, let's say, it's gone to 27 degrees, which added 10 millivolts, because 5 millivolts per degree, I will measure the temperature inside here and I will minus it in the software, whatever the temperature reading of this MCP9701A. And that gave me the best results, because no matter what the case temperature is, it's always compensating for the change that the AD495 is compensating, thinking it's doing the right thing, when in fact is actually doing the wrong thing. Okay, so the other reason why I put two 5-volt regulators was because of the TM1637. Okay, when each time it does the sequence in turn to put on the segments, the 4 segments, it actually loads it was loading the 5-volt line. And every time it loads the 5-volt line, it's creating pulses at the load frequency of this TM1637 timing. And the PIC chip was seeing it on the 5-volt line. So therefore, I was having a very bad result on the analog to digital converter being noisy. And the noise, I'm showing it here on the oscilloscope. So I've got the oscilloscope set to on AC, okay, so I can zoom in to the pulses and go down. I went down to 50 millivolts scale. And actually I am having 50 millivolt peak to peak noise load on the 5-volt line. But what you're seeing there, you're seeing one voltage regulator, which is this one, the second one running the TM1637. I called it VCC2, and there it is there. And the top line is VCC, which is the first voltage regulator that's running the PIC chip. And you can see how much more smoother, that's on AC as well, at 50 millivolts, okay? You're not seeing the same noise onto that line. And if you look closely, you can see a little bit of it, very faint, okay? And that's because there's communication between the PIC chip and the TM1637. So every time it's talking to it, you can see slightly those pulsing there. But if I stop it, okay, stop the oscilloscope running, you can see that it's 4 pulses. 1, 2, 3, 4. A break, 1, 2, 3, 4. And that's every time is the display is running on its own, and also when it writes to it. Anyway, the only way for me to stop that is to have 2 voltage regulators, which I did here in the circuit. And that solved. So my analog to digital converter now is more clean than the original testing on the test board originally when I had that test board running. Okay. So that's how I solved it. Getting back to the circuit. So the other part that I've changed was the LED outputs. I've put them on this on the RA0 and RA1, and that's the in-serial circuit programmer as well. 2 lines, data and clock. And I did that because I wanted to use another analog to digital converter for the MCP9701, and I wanted to put a capacitor. So the only input I had left was RA3, which hasn't got an analog input anyway. So that's why I swapped those around. I removed them from RC1 and RC2, and I've put them on R0, RA0 and RA1, the LEDs, which is one LED over here. It's just a bi-LED, that red and green. So that's green, sorry, and now it's shows red. And just to show you as well, that when I move the I don't know if it shows it here. Yeah, you can see the red LED goes bright every time it goes to the interrupt, okay? And so that's an indication that the movement switch is working. So I've done that as well, like that. I also added a 470 nanofarad capacitor on the switch here, okay, onto the switch. Now I said originally I don't get switch bounce, but if you don't use a tactile switch, these type of switches, I actually modified this and I did put a tactile on it, but the original switch is a very cheap terminal, doesn't even latch properly on the terminals, and it affects the code. It's not really designed for digital microchips and communications or reading switches. So just to help with that, I added a 470 nanofarad capacitor. So technically, if you use a tactile, you don't really need the capacitor, but I added that, and in the software I added a little bit of a pause, okay? Just a 15 millisecond pause. If you use a tactile, how I said, you probably can pretty much don't need it. So, and the triac driver, which I use the BTA12, by the way, I changed the resistor, the correct resistor value is 750 ohms. So this LED runs just a bit more than 6 milliamps, 6 to 7 milliamps, okay? And the rest of the circuit is pretty much how I originally set it out. And the other part that I didn't really need to do this here, but I added a 1K from the VCC, okay, to the pot. Only just in case when you're working on it, you might short out the 5-volt line here, which really I didn't really need to bother, because this voltage regulator have short protection and over temperature protection anyway. So really, I probably didn't really need to do this. I've done this wasting my time here. But for some, depends on what systems you're running. For example, some microchips that you might use the actual voltage out from the chip, might not have short protection if you run it like that. So it's good to put a resistor there. See, so this pot, something goes wrong, you cannot short out that line. But I added a capacitor here as well because of the resistor, just to smooth it out again. But because of that, now I've got less voltage under 5 volts on the pot. So the software, I had to do a little adjustment there to make sure I am still reading from 0 to 500. So I'm cheating slightly with the software, because the software thinks it's reading 0 to 5 volts and it's actually reading 0 to maybe 4.5 volts, okay? So that's that. So this is the actual final circuit. As you see it, is what I have in the soldering iron circuit, okay? So finally, I come back to the software and try to finish off what I've changed. So the first thing I've changed is the timer 1. Originally, I used to go to the interrupt to measure the temperature of the soldering iron every 111 or 112 milliseconds. I'm going to the interrupt now every 31 to 32 milliseconds, okay? So I've changed timer 1 from 10,000 to 50,000, okay? And the calculation of timer 1 is written here. So the word value, which equal to decimal 65,536 minus the 5,000, will give you 15536, and the prescaler is set to 1 to 2, all right, every second time here. So then you times that by 2, because that's what this prescaler is. You get this figure, you divide it by 1000 to get the 2 milliseconds, and you get 31.072 milliseconds, but in reality it's around 32 milliseconds because the time of the interrupt routines, okay? So I've made it quicker, 4 times faster going to the interrupt to read the temperature. So that has improved it a little, and improved reading the switch as well. In the beginning, it flashes the, and I'll just show you this again, it flashes, as you remember, the figures there. First it flashes the tip correction, which is 12 for my environment here, my soldering iron, and then it flashes the temperature reading setting, which is a Z. I set it to 0. This is doing the averaging right now, and calculations once you switch it off, and that's why it's taking a bit of a while there, because of the loop that I have in the main loop, okay? And the other thing that I've changed is when it flashes there, that's the time you can set to change the tip correction. And I've done it in here in the software. if the set switch is held down, okay, and you turn the power on at boot up, it will go to tip correction. And I'll just show you that now, okay? So if I hold the button down here, put the power on, the LED flashes, and now I'm in tip correction. So I know originally I had it at 12, so I set that back to 12. Press the button and it continues on at the loop here. So then it flashes the temperature set temp. And originally in the software, I had it where I created my own delay time pausing, but because the interrupt haven't started, I just changed that and I just put the Pig Basic Pro command pause command. This command, how I said, it stops the interrupts, but because the interrupts haven't started yet, I could do that. The reason why I did that is to save code space. I think it saves one word each time in this situation. So, and also I had a bit of a bug where I forgot to turn on timer 1 in the beginning. So until I pressed the switch, sometimes it was not going to the interrupt because timer did not start. So I make it start here, T1 con.0 equals 1. The main loop is still pretty much the same, except I have created the averaging. I modified the average file. And what I did, I've made 2 sets of averaging. One is for the temperature reading of the soldering iron, okay, thermocouple of the AD8495, and the other one for the pot. Now originally I was still getting away with it with just having the one value, and I had remembered that name value, but because every time you press the button here, okay, that's the temperature there, and that's the LED putting the element on, okay, so you see when I've got it at 0, the element is completely off. Every time I change back here, okay, that's the, of course I had the element on, so it's warming up. I was getting, it needs to re-average the value again for the AD8495 each time I change from that point to that point. And it was annoying me. So I thought, okay, getting back to the software is to have an average, separate average for the pot reading here in the circuit, and have a separate average for the AD8495. So all I did is copied the same functions here and just gave them 2 names, value 1 and value 2. And these commands here, let's say this one, current average, I put a 1 there, and then after I added 1 of the same, copied that and gave it a 2. But this part, the constant ones, because it doesn't change anyway, I didn't need to create doubles for those. Okay, I'm using still the same ones. So in the code, I got average 1 loop type of thing and a return for the go sub, and I've got average 2 and a return for the go sub. And each part here, I see I've put the 2s, so I know it's for that. So now I can measure 2 separate averages without conflicting until it does the average again, okay? So that's the other part that I've changed. And in the tab settings here, Originally, remember, I had something to do with the LED staying on when I had the blue LED test board running. And let me see here. Okay, it wasn't in the temp setting. I think it was in the tip correction. Because originally the tip correction loop used to run when I'm in temp settings, which I have changed it, okay? Now the tip correction only runs at boot up if you hold the set button down and you turn the power on, okay? So I've changed it to that. So now the tip correction only runs at boot up, okay? So this doesn't, but originally when it went to tip correction, it flashes the LED. Originally I had it 7 times. I just changed it to 5 now, so I need to change that. Show to say it's 5. It's not important. And it's not Y200 degrees actually. That was another idea that I had, and I removed it. When it came from the flashing loop, the LED would go off. So I needed to put it back on to tell me I'm still in the tip correction function, okay? Which is the red LED now there will change to a green. And originally on the test board, I had a blue LED, okay? So that was the how I fixed it. I needed to put the LED back on there, and you see it said blue, but in actual fact now it's actually green, but just put LED on. The set LED needs to come on. Set LED on. Yeah. So then, because I've got 2 averages now, I had to, before I go to the average, okay, you'll have to tell value 2, which is used in the average 2, which I showed you here on the average file. Average 2, which is here, uses value 2 as the value. So I had to tell it the tip error value loaded onto value 2 and goes up average 2. But when you come to display it, I had to again change the value of the LED file. Originally was called value as well, and I didn't really have to do that, okay? But now, because I'm using 2 averages values, now I have to say value 2, which belongs to, at the moment, the tip error correction. Or if you're in the temp settings, it will belong to the tip setting, the pot value, okay? Same here, this is the pot value, but of the tip correction. When you display it, you need to tell the LED out, okay, to show the value 2. So then, not to make it confusing, the original value name I've changed to LED value. So if I go in the TM1637 file, this used to be called value here. So now it has been declared as the name LED value, okay? Because that's what we're displaying in the segments. So back to the software, main code. Then, of course, I had to add this extra line again here. So that's the change that I had to do. It's just common sense, but for anybody is looking at this. By the way, if anybody is interested on the software, if I don't know how I can upload this software if anybody's interested in it, but you can let me know in the comments, and I'm happy to share if anybody's interested of having the software or the hex file. I'm happy to share that if they provide me a place where I can send it or upload it, okay? So, and in the tip correction, by the way, I had to read the switch separate to the interrupt, because originally, when the interrupts are running, every time you press the switch here, on the interrupt on change, it goes to the interrupt anyway, regardless of the 32 millisecond interrupt time. But because the tip correction is done at boot up, when the tip correction is made, the interrupts are off. So I had to read the switch in the actual loop itself, in the while loop. So I had to add these lines here to read the switch, okay? And saving the value of the tip error in memory, okay, is done in this function here. So anyway, that's that part. I think the rest I did show: the flash LED, go subroutines, the delay routine, and flashing the LED display segments routine is done here. But the interrupt here, I've done some changes here as well. So that's when it's reading the switch, read set switch if pressed, okay, on the interrupt on change. And the interrupt LED comes on. And here is where I'm reading now the enclosure temperature, which in the circuit here, I'm reading this analog input, the MCP9701A. So first I read that, and that is the actual voltage on the voltage regulator, okay? You need to do that if you're using the external voltage as a reference. You need to put a voltage readout of your multimeter here, an accurate one, and place it into the value here. So that's 4.993 volts, and that's written in millivolts, okay? And enter it into the enclosure temp value, and then I gotta do the calculation. Now, the calculation, if you look at the data sheet of the MCP9701A, if anybody's interested, that model, the 9701A, it's 19.5 millivolts per degree, okay? That's what it outputs on the pin there. But 0 degrees, at 0 degrees, okay, it's been calibrated at the factory, it outputs 400 millivolts. So you have to actually minus the 400 millivolts so you can start reading temperature from 0 degrees onwards. So that's how I've set the formula, okay? So the enclosure temp equals minus the 400 millivolts. So now I am at 0 degrees. The reason why it's times 10 here, because as you know, this is not C programming. And this hasn't got float and all that. It doesn't read points. So just to get the 19.5, I'm timesing that figure there by 10 and then dividing it by 195. Okay, so I'm pretty much dividing it by 19.5, but I can't put a point, so I had to write it as in millivolts times that figure by 10 and then 195, which is if I times the 19.5 by 10. Okay, so that's why I had to times the answer here, minus the 400 times 10. Okay, so that's why it's written in that way. So now I'm reading whatever the temperature is from 0 degrees, okay? That's the first thing I did. Then I'm going to read the actual temperature of the thermocouple of the AD8495 module, okay? And the voltage reference obviously is the same because it's whatever the peak chip voltage input is, and that's what it equaled with the particular voltage regulator that I've used. Now I'm going to minus the error of the case inside because I'm measuring the temperature. So then I said, if it equals to 24 degrees, so once this builds up to 24 degrees, okay, inside, I'm saying, or above, start doing the formula, okay? So if it's the case temperature is at 25 degrees, pretty much, or I'm actually lying, at 24 degrees, what I've said. Originally I had a 25, but I found that I was 1 degree out, comparable with my temperature indicator. So I've changed it to 24. And so I did temp equals, okay. Now at this stage, this temperature of the thermocouple of the AD8495, this is the voltage that I'm reading, okay. There it is, temp equals whatever the voltage is. I have not done the formula of minusing the 1.25 volts of the voltage reference here and then dividing it by 5 millivolts. So at this stage, this is just voltage here. It's not actual temp in degrees. So temp minus enclosure temp minus 24. So I'm minusing the 24 degrees that is inside here. So if it's 25 degrees, then it's going to be 1 degree because 25 minus 24, okay? Enclosure temperature, let's say 25 minus 24 is 1 degree. Now we know that 1 degree on the AD8495 equals to 5 millivolts, okay? So because this formula is giving me degrees, not voltage. To change it back to voltage, I times it by 5, which is the actual 5 millivolts. So the answer of the temp is still in voltage, not in degrees, okay? That's why it looks like that. So it might look a bit confusing. And I wrote here, temperature still in voltage, has not been calculated to degrees. That is why times 5, okay? But this is my way of doing it. This is the way I've done it. There's probably other formulas if you're writing the code in C, you know, and you probably won't do it in this way. But this brings the result, the correct result that I need, okay? And only do it if it's equals to 24 or above degrees in the temperature, because below that, then the AD8495 will give you a correct reading. So that's the only time I need to do it, because I'm fighting back the error of the compensation, and then, okay, which I didn't have before. I wasn't reading below 0. So the only way I could do it in Peak Basic here, Pro, the below 0 formula had to be calculated first. And I say, if the temp, which I'm running in voltage, right, is smaller, because I haven't done the calculation yet, then 125 volt means it's below 0 degrees, okay? Then temperature, which is still in voltage here, now we're going to change it to degrees, okay? 125 minus the temp, because now the temperature will be below 0, so it will be below 125 of the voltage reference, okay? Dividing it by 5, now I just changed it into degrees, 5 millivolts. Then I say, if the temp is below that, change the C letter that I have here to a negative, to a dash, indicating I am below 0 degrees, below 0, okay? And I've made it only changes the negative once it becomes 1 degree. Now, it will become 1 degree when it's equals to 1245 or below, okay? Because each 5 millivolt is 1 degree. So then I've made it 1245. I took 5 off and changed the letter to a dash, indicating a negative. Then I don't want to do the above 0 degrees formula, so I said go to jump, and I will not do this function here. You can come up with another way of doing this, but I've just done it in that way, okay? Simple for me. Bypass this. If you're not below, if you're above 125, then you're above 0 degrees, okay? You don't do this formula, you do this one. Then the code will come here, and I'm telling it to set it back, set the letter back to C, just in case it was a dash or a negative. So that's what I do there. And so I wrote here, do not set letter to C in temp setting mode. Also, if I'm in, so if you're in setting mode, okay, which will become 1, then don't keep changing this one. So then you do the normal formula that I had before. Temp equals temp minus 1250, the voltage ref divided by 5. And I have transposed the voltage to temperature. Okay? And then I do the error correction, the original error correction that I had before regarding the soldering iron when it's heating up. Just to remind you that the temperature here, the thermocouple, is going to be hotter than what the tip is. And I've made it, if it's greater than 50, okay? So if it's under 50 degrees, it does not actually do this error correction. And also, and you can write this in this way if you want, the same as C, as the same thing, okay? But I'll go back to original of Pick Basic. Set temp needs to be greater than 1. So when I go to set temp here, at 1 degree, okay, the pot's a bit touchy there. At 1 degree is not going to do this function here. It has to be over. So now I'm at 3. Now, plus greater than 50, it will do the compensation. So once I've got it at 0, okay, when I'm running this soldering iron as a temperature indicator, I don't need the tip correction because the element's not running. I don't need the tip error correction, okay? So best not to do any errors anymore for temperature indicator. So as a temperature indicator anyway, it does not minus that. Otherwise, you'll have a wrong reading. And so that's that. And the rest is as it used to be. And for the clock counter regarding the timeout, when it goes to sleep if no movement is sensed on the soldering iron, okay? Because I'm going every 32 milliseconds, okay? 32 times 32, it happens to be coincidence, gives you roughly 1 second, okay? So the ticks every 32 milliseconds that it comes here, I have to times that. Not times it actually. When it reached 32 times of 32, so 32 times 32, then 1 second have gone past. So before I came here to the interrupt every 112 milliseconds, so I had to only times it by 9. Sorry, I had to put 9 here, which means it would be times every 9 time you created 1 second's gone past, okay? So what I haven't explained was the when it goes to sleep. So over here, once the minutes become equals or greater to the timeout, and if we go back at the top of the code, I set timeout con 30, so 30 minutes. So for now, I'll just set that to 1 minute, okay, just to show you the what happens when you're not moving the soldering iron. Again, you can see when I move that, the red LED flickers, okay, brighter. The sense movement is working, okay. So I'll compile that and I'll program it. So now we'll wait 1 minute and it should go to sleep. So I probably will be speeding up the video. Okay, so 1 minute has gone past and it actually has gone to sleep. And if that was heating up, it would have stopped heating. Now, if I touch the iron, it will come back on. Okay, there you go. It's back on. So if I set it now to the temperature, it will go to that figure, 300. And the other interesting part is, since I've put everything in the case, and before I was using this lead plus the original lead in series, okay, with it. The tip correction is much less. It's actually only 7 degrees now. Before it used to be 12. And now I've realized that I had to set it down. So once everything is installed and with the proper circuit board and the wire connected there, and I have a, so the calibration must have changed. And you see now it's regulating, okay, to 300. And just one more test, okay, with my meter here. If you could see that. Let's see what I'm doing. Put some solder here. And put some more solder. Come on, I'm at 99 there. I'm sure it's 300. There you go. It's a matter of the thermocouple making proper. Okay, now it's making proper contact. It's 300 degrees. Okay, so that's spot on. Okay, so anyway, also I wanted to show you is the when it went to sleep and it had the dashes. Okay, that's done in the TM1637 file, and it says here this sleep flag. If the sleep flag is a 1, the segments equals to 40, which means set all the 3 digits to a dash. Okay, so that's how I done that. I done it through the actual other file, putting that line there. So that's how that's done. So pretty much showed pretty much everything. So can't put it back to 30. What else I wanted to show you is regarding the soldering iron. I did a little modification here. This circuit board originally, okay, I've put it in with the wires. But of course I did know back then when I put it in that it had no support. So these elements, the case here, have a screw here, have a grub screw, plastic grub screw, that tightens onto the cable. Okay, which stops the cable pushing on here. But the Weller one hasn't got that, because originally the Weller has this sort of thing, yeah, and that squashed the cable there, and that screwed to that. But of course I'm not using this, it's not suited for this. But what I did, I've made a small bracket here. Okay, so that's the circuit board. I made a bracket, just screwed it onto there, and a nut, and I drilled the circuit board. I put a plastic washer there so it doesn't short out here, and the screws from the top here. Okay, and so now that circuit board is solid with the casing of the element. Okay, now the other thing that I did, because this element, right, having a longer element and probably filled with some ceramic, I'm assuming. I can't really have a proper look, but it does get hotter around here. This part does get a bit hot. I can't remember if it could get to around 70, 80 degrees. I can't remember because I did test it. So the original Weller doesn't get that hot because it's designed different, okay? The original Weller, the element is only down here, and this is not filled with anything. This has got the thermocouple here, so this is filled. So because of that, the temperature, that's the tip. This is a different tip that I've put. So a lot of heat gets to there, and so what I did, I had a spare cover for the soldering iron. I made a bit of a template here, which that fitted in there, and I drilled some holes for the vent to try to cool this back section. Okay, so I'm gonna give it a sand, and then I'm gonna polish it on this. Okay, and I polished it up. You can see there, it's much better than before. But in actual hasn't really made that much difference. Maybe cut 1 degree, that's all. So it's pretty much useless. Doesn't help. Also, it's very close here. This hasn't got much gap inside. So originally, these elements, the handle, okay, have like a spacer. Have a spacer to space this off. You know, a couple of mils. And obviously, that's because this part gets hot. And so what I did is I got these fiber washers, okay, from AliExpress, and they were the perfect size for this. So I glued 2 together with super glue, okay, and did that. But what I did, I offsetted the holes. So the original holes here, I mean the screw points, that's screwed into that. I didn't still with the spacer, right, because the screws might get still hot and is going to carry the heat into the plastic holder. And because this is not designed for this element, I didn't want to take the risk in ruining the plastic here, because I think the original handle of these things is more like bakelite, and I think this is more plasticky, okay? Because, how I said, the original Weller doesn't really get hot at the top here. It runs pretty cool. So what I did, I glued, how I said, these 2 fiber washers together, and I screwed into the original mounts. Then I offset it next to it, and I glued another part of the washer, fiber washer. So it's like 3, and that's the spacer. Okay? And so spacer and a spacer. Okay? So the screws that screws this, it's in the fiber washer. So if it gets hot, it's not going to damage the plastic holder. Okay? These fiber washers normally can take heat as well. So that's what I did there. So that was a little improvement. A bracket to hold the circuit board to this, and the spacer here, and not having the original screws screwed onto this. So okay, you can see it better there. That's the hole there too for the screw of the bracket. So now that pushes into there. Okay. And I have to line it up. Goes this way. Okay, let's see. It's just the circuit board. I think it's just must be hitting something there, but no, it clicked off, so it's much better. So you can see now the holes, they go into the fiber, and the fiber washer holds with the original screws there. So the screws do not touch as well to that. Okay. So now I had to find some screws, and I managed to find some. Okay, so I'll put the screws back. Okay, and that's what it looks like. Okay. So now it can cool as well around here because it's got an air gap. And one day, if I fix the other element, I'll maybe put it back original, and then I won't use the spacer. Okay. Okay, I have some ice here. So now I've got the temperature to 0, which means It's a temperature indicator. Four degrees, 3 degrees. Of course, ice is at 0 degrees, so -1 probably is all that we're going to get. The soldering is right melting into the tip, melting in between the ice. Okay, so there you go. We're reading below 0. Pretty good, I reckon. Okay, now we'll put it back up. Let's go to just 50, yeah? 50 degrees. You tell me which soldering iron can do 50 degrees. You cannot buy one. But it's actually regulated to 50. Within 1 degree. Pretty good, huh? So yes, I have range from 0 degrees to whatever degrees I want. Of course, if I cool it down, okay, and I set it to 10 degrees, once it gets to 10, it should start heating up. So because that's what I've set it, right? Yeah. So I'm back on the ice. Should start coming on now. There you go. So now it's going to maintain 10 degrees, and I've got it on the ice. See, it just pulses very quickly now. There you go. Of course, it's going to go up because it's going to go to Tempian, and Tempian is higher than 10. But because I was cooling it with the ice cubes, it'll take a bit of a while. So that's it. Thank you for watching.